சந்தோஷமாக சுதந்திரமாக
components of transmission system you have studied earlier. This semester you have a course called your design of machine elements, right? As I told you, each and every element, as the morning sessions we are discussing about the vibrations and other things, how to eliminate vibration. If not, before you understand how the failures take place, professor might have covered your first unit with the different kinds of stresses that takes place in your each and every members. What is the form of stress and in what way it is going to affect the life of the individual component. So as I told you in the morning also about you need to know about before you apply a load in a particular member, you need to understand the design. As you know, the design is nothing but arriving at the particular dimension. What is the output of your design? You perform a design, right? You perform a design for a particular engine component or some component, machine component. What will be the output of your design? Product. Product means you will give the product in hand. You will get. Can you define design? Can you define design? The person asked me in one of my interview. Can you define design? Model of a product, someone goes. Define design. I am asking a basic question. What is design?
Complete plan about the product.
Complete plan about the products. What will be the how you will present the plan? How you will give me? So I am asking you to design on the machine component. So what you will give me? What is blueprint? Drawing. That's design. Actually, the output of design is nothing but your dimension. Design is output is design dimension drawing. What we call it as dimensional dimension and drawing. So the dimension and drawing. So your procedure, what is design is a procedure of obtaining dimensions and the drawing of a component, considering the material and its physics, how it is going to work, what kind of a force is going to take place, in what way you are going to connect that with some other components, what are the things that is exposed, whether it is exposed with a temperature, whether it is exposed with a compressive load, whether it is exposed with a fatigue load, all these things based on that. So you cannot use the same material for some component which is going to be exposed to compression load, and the same material cannot be used where we want a fatigue load. You know what are the different types of material properties. The material has different compressive strength, different tension strength, different cyclic loading strength, that is your fatigue strength. So the main consideration that you do during a design process is your material. So if you are using a chair, right? This is a very good design of the chair. How this dimension, the thickness, and how this is obtained. Some other artistic work or something else is there. We need not worry about the things. Thickness and the angle and other things. What are the things considered? If it is a plastic, you can make this thickness. If it is in wood, will the thickness be sufficient? So the material properties play a vital role in arriving your dimensions. Your component, if the component is made of aluminium, its dimension needed for a particular strength is different. Whereas if you use or replace it with a steel or something else, your dimension is different. So you start your design procedure by understanding the material and the material's behavior. And the second one is you parallelly substitute what are the different kinds of loading that takes place during, that is something called as your multi-physics model. In a model where you think about different physics, what are the force, what is the temperature, what is the electric thing, what is the electrical kind of thing going to work there, whether I need an insulator for heat, whether I need an insulator for temperature, all these things are considered. So your design is a complete, output is completely nothing but your drawing, as he was telling about a blueprint. In short words, you can tell about a blueprint which consists of the dimensional drawing. So you come across different types of component, but so as I told you, it is a procedure to arrive at the dimensions. So procedures are standard. So So what is there to teach in a design? That is the question. In a design, a design process can be automated easily. You understand? A design process can be easily automated. How it is automated? You have a program. You write a program for a design of whatever design you have studied so far. Design of knuckle joint you have studied. Design of knuckle joints. Not yet. Anything else? Design of couplings. Design of couplings. So there is a need for what is the need of a coupling to transfer the rotary motion to a rotary motion to transfer. So you need a coupling that you want to do. So you will be giving about what will be the maximum power that is going to be getting transferred and what will be the RPM at which it rotates. So based on that you will calculate what is the stress, maximum stress that is going to get induced and whether the material will possess the stress or the stress that is created during the operation is less than the permissible stress of the material that the design is good. If not, then you go for a modified design or you change the material or something else you do, some alteration work and again you will do it. So but in case of, you are going to discuss about something called as a connecting rod. A connecting rod is an important element. So we are going to talk about, this is one of your syllabus movie, right? That had very large engine pistons. So a running component connecting the crankshaft to piston in trunk piston engine or to the crosshead in crosshead engines. It has both linear reciprocatory up and down motion and rotation motion. It is something called as a combined motion. Why we are concerned about what kind of motion it takes place? Because in different positions it is going to get the force transferring in different directions. And your material is going to be subjected to different kinds of forces, which is going to give rise to different kinds of stresses and different locations. How you are going to deal with the material? How you are going to deal with the dimensions? And this is again in an assembly unit how you have your connecting rod fitted with a flywheel. As you know, it is connected with a flywheel. And the primary function of this to transmit the push, the pressure or the thrust of the piston, the crankshaft, either directly or indirectly. So what is the connecting rod's main purpose is to transfer the motion. So transfer motion is how it's going to be. There will be a pressure or thrust at one side. It is in the piston, or sometimes it may be by internal combustion, or sometimes it may be by gas or fluid pressurized. So based on that, a piston is going to move. So the linear motion is going to get converted into a rotary motion from one end to another end. So you have a different kind of combined motion, a rotary and a linear motion is to be combined at this point. So the secondary function is in most designs to convey cooling oil to the piston, which demands for a quite large diameter mass. This one. So the requirement for a connecting rod, what is the next secondary process of the connecting rod is you have the piston head. If the piston head is used for a internal combustion engine, so you know a diesel or any other fuel is going to be fired inside. Its combustion, very high temperature is going to get generated and that will be dissipated to the piston. So the piston should not be allowed to overheat. If it is getting heated, what happens? If the piston is getting overheated, what happens? You get a sticky friction condition. The piston balls will get sticky with your cylinder inner liners, or the piston can even wear out easily, or sometimes the piston can get overheated, may due to its thermal expansion, may get sometimes you can see cheesy, engine cheeses, somebody else's engine cheeses. They take some kind of a material like sugar, sugar what you add in a petrol or something, you combust, it gets a sticky and quick instantly gets the see all these things. So what is our idea is to reduce the temperature of your piston. We need something else, a fluid to flow inside nearby the vicinity of the piston and need to come out. So we need something like a cooling oil circuit need to be done. There is a hole from the big end to the small end. There will be a small hole through which you are going to have your cooling fluid can be moved across. So the types of piston is a marine type, the large end, that is a T-shaped end. You have a T-shaped end for your connecting rod. So you can see this one, right? It's like a T-shaped end here. Connecting rod is the big end is connected in a way like this. And this one is called as your marine type connecting rod. It's like called as a marine type connecting rod. The next type is the fixed center design. The upper half of the crankpin box makes part of the connecting rod. An alternative design connecting rod with obliquity split large end. So you can see here, this is a different obliquity, and you can see how upper half of this big end rod, the connecting rod, by means of a fastener. These are the two things that we have. So here you can see the oil hole. Can you see the oil hole? It will be there throughout. From here to big end to a small end, you have the hole inside for your oil. For lubrication as well as for cooling, you can use it. So this is a fixed center connecting rod, as you see there. And this is the fork and blade type for V engine. For a V type of connecting rod engines, you have this fork and blade type. So you can see like this, right? This is called as the fork and blade type. Where you have blade, it's something called as your blade rod cap. It's a blade rod cap. And these are all journal bearings. Separately you have the journal bearings here. And this is the blade connecting rod. And it's the large end being disintegrated, and that way you can get connected. So we engine connecting rods, fork and blade type. It's called as a fork blade. And next is your articular type. You can see this is a articulated type connecting rod. Or you can see it has a different kind of hinging over here, and likewise you have different, and it is separated here, and that way you can tighten it by this. There is one fastener over here. Here there is a pair of fasteners on either side. You can fasten. So the elements of these kind of connecting rods are the major elements. This is the small end bearing. You have a small end bearing, and what else you have is you have your rod shank, and you have your foot over here, and there is bolts and nuts, and you have the upper half of the crank pin bearing and lower half of your crank pin bearing. So the crank pin end is bottom end bearing, lower end bearing, big end bearing, crank pin bearing or large end bearing. So you have different kinds of bearings. The bearings need to bear the load. Need to bear the load and bear the forces that if it is subject to working with the component. So the attachment point. So attachment point for a crank pin carrying a bearing, and it consists of two half removable shells in a marine tank, held together by bolts and nuts. The shells have a lining of bearing metal white lead to provide for an anti-corrosion layer. So it's simply we look at that one is made of a single material, but there are different kinds of material that will be supporting or helping you for avoiding wear and tear, to use it for very long life of this kind of connecting rod. And the bearing housing contains cooling oil grooves, where you can see that here the housing of the bearing have your cooling oil grooves, where you get your oil flowed from throughout the hole to get its temperature reduced. Between the foot and the box bearing housing, there are sims, distance pieces, compression sims, compression plates for adjustment of the cylinder compression. So if you want to see here, this is something called as your intermediate plates, where you can adjust by using different kinds of thickness. You can adjust the center to center distance, and that can also be adjusted by means of using sims. Sims, you know, these are very thin leaves of material that is having very good compressible strength, and it will not get plastic deform or elastic deformation. It is used for increasing the length also. So next is your rod shank over here. So it is also called the body and may take up different forms. It has a drilling throughout its length. You have a drill, you can see the drill's continuity from here. Here it starts drilling, and throughout the length it has a drill over there. So next is your gudgeon pin end. So your gudgeon pin end is your upper end bearing, top end bearing, or small end bearing, or wrist pin bearing. Can be called in a different way. So the upper end bearing is a bushing having an interference switch nip in the eye bored in the rod. So So you can see here, right? Here it is a board and it has a small hole also over here. Board in the rod. The eye is a single piece bearing bush or bushing pressed into a sleeve. So it's a single piece of bearing. It will be pushed inside that one to have separated from your rotating object so that the wear and tear does not increase. So the bushing is of bronze or of cast steel and centrifugally cast bearing material. What is that centrifugally cast bearing material? What is centrifugally cast bearing material? Any idea? You study casting? Centrifugal casting, have you studied? No. So it is something like, see, if you are going to cast it, you are pouring a molten metal inside from the center in a rotating die, right? In a rotating die, you pour molten metal inside. What happens always if you are rotating a fluid or something else inside a cylinder, it will have a centrifugal force and it will try to come out in radial directions. So instantly what happens, the first layer of metal will be the extreme large diameter it will form. Again if you pour metal, that will form the next layer of material. Again if you pour, it will be the next inner. So the material will be always forced outside because of its centrifugal force. So what happens, the material's densiest part will be the outermost surface. And when you are moving towards the center, its density decreases, its grain size also decreases, it has a different grain growth and you can drill it again and you can take. So this is a centrifugally cast bearing material. Either it may be a cast steel or sometimes it is made of brass. So people, they want the density to be in the higher the outside and the density in the inner side, they are not concerned about. And the stresses, what are the different kinds of stresses that take place in a connecting rod is your axial forces resulting from gas pressure and inertia of the piston assembly modified by the side thrust arising in consequence of the connecting rod. The maximum load is in compression. What is the axial stress, the axial force that takes place? So your piston is moving towards the compression, full compression at that time. Your piston will be what? Straight. Your piston will be straight. Straight towards the thrust force. It will be equal and opposite to the thrust force. The maximum compression takes place. So the force will be acting along the axis of your connecting rod. So that along the axis of the connecting rod, if you have your force working, that is called as your axial force. So it can be equated with what is the gas pressure inside. In the piston, whatever the pressure, what is pressure? It is force per unit area that will be transferred to your total cross section of your connecting. And the inertia of the piston also sometimes gives rise to this axial force. What is the inertia of the piston? For example, you are forcing the piston to a one particular end, but it does not. So you are throwing the piston out, and then you are pulling it back, right? You are throwing towards the compression, and then you are pulling back. Due to the velocity with which the piston moves towards the cylinder, towards the compression stroke, while it is returning, it has its own weight moving outwards. That is one inertia force. So your what happens? There are two forces acting. One is your piston will pull your water. Because of the inertia force of the piston will pull your connecting rod, and because of the thrust force acting on the other side of the piston, it will push your connecting rod. So what kind of, so this axial force will be fluctuating. Your axial force is not the same force throughout the running of your. So throughout your forward stroke and your return stroke, in between all these things, your force, axial force is going to change its direction. The maximum axial force will be very heavy when it is in the compression state. It will be the maximum compressive at the top dead center, and sometimes again it comes back. During that time, the force may not be there in that direction, and again if you are going for compression, it will be acting in the opposite directions. So the tensile stresses occur after firing due to the piston inertia. While it is firing, the tensile stresses takes place because of the inertia. As I told you, when the piston tries to go out of the connecting rod, there will be a tension force created inside. Bending stresses can occur after firing. So once the firing is done, what happened? Actually, the piston is not going to retain in its horizontal position. The piston is not going to be inline. Now the connecting rod is not going to be inline straight. It is going to bend, right? It's going to rotate for 10 degree or 20 degree, 30 degree. at the time whether the force is going to be acting in a tangential way. So you are connecting rod, right? So see, if you imagine this as the piston base. So during compression, the piston is in straight form. So your force will be acting along my hand in the straight line. But during return, what happens? The connecting rod bends, but the force is acting in this direction. And here there is another force, but the connecting rod is not in line or not collinear with the force. So there will be a bend. You understand? There will be a bend in the connecting rod. And the transverse forces, so we are talking about axial forces, so known as dip are caused by the inertia effects of the rod. The connecting rod itself possesses a mass, as we are building it with a solid. It has its own mass, and that also is going to have a inertia force. So fortunately, axial and transverse forces do not occur at the same time. This is again by virtue of its mechanism, how it works. Your axial force will work only during what position when it is straight, either in the top dead center or in the bottom dead center. The piston will be in the straight condition. Sorry, connecting rod will be in the straight condition. At that time, you have your axial forces, and your transverse forces, due to the inertia effects of the mass rod is not working during that time. It will be working in the other angles of your connecting. Next is about lubrication. So it is carried out through the shank bore drilling and running throughout the shank. It conducts oil from the big end to the small end for lubrication and to the inside of the piston for its cooling. So this for connect your lubrication. So lubrication is for what? Reducing the friction. Whereas your cooling also takes place with the same lubrication. So it is a combined action. So you have your cooling as well as your, so the conducts cooling, conducts oil from the big end to the small end for lubrication and to the inside of the piston for its cooling. How this lubrication is going to get work as a cooling? The lubricating is an oil. So if the temperature of the piston is very high than the very much higher than the what is that? Your vaporizing temperature of your oil. The oil may get all the heat absorbed and it will get converted into different form like your gas. So whatever the heat will be taken from the piston, that's how it's going to happen in your lubrication will be acting as a cooling fluid. So you can see this is the fully machined connecting rod. You can see how there is an yellow color line. This is your oil, right, where you get your cooling line or your cool that is drilled over there. And you can also see over this is an oil spring pressure distribution caused by your forces in big end bearing for your Wärtsilä 64. It's a kind of finite element analysis where you can see how the oil pressure is distributed through the bore. The bore drilled in the latest Wärtsilä 64 engine. So this is one kind of a bore. How the oil is allowed to move from your big to your small end. Withdrawal or pulling out or removal. So in most designs through the upper end, in few designs the piston and the connecting rod are withdrawn downwards. So the piston and the connecting rod are sometimes moved in the opposite directions. So the application wise, where you see your connecting rod is used is one is your IC engines. Main jet is in IC engines. There you see the explosion is very heavy and it is the energy is spontaneously ignited. You have a massive pressure that is created on the valves. And second one is your steam engines, and your steam engines are not so dynamic as your your exploding IC engines. Your steam engines, the steam is going to fill, so it takes a lower time than your combustion ignition. And the functions of this connecting rod will be used to transmit power, or it is transmit power means from a reciprocating motion. It's going to convert into a rotary motion. So it is going to transfer power from the fluid to the another end in a pipe or in a crank. The shape is I-shaped section mostly. Preferably you can see most of your cross section of your piston. your connecting rod will be of I section. Why they go for a drop course. So you see your casting and your other processes cannot give you very close grain structures to have very high strength, and there should not be any defect, not even a single inclusion, there should not be any porosity. So you should have a uniform grain structure. It's like a different kind of a grain structure or material movement that is needed to have a very good strength of your connecting rod. So your connecting rod is done by a drop forging, but it is in different stages. Initially it will be made in one stage, and then it will be annealed, again it will be made in a different form. So at the end you will get the final shape of your connecting rod. So the design of connecting rod is based on the compressive load due to buckling. So always design for the highest load, right? What you design, if you make any design, the component should withstand the maximum force that is going to exert. Either it is a compression load or a tension load, you need to concentrate on the maximum one. So the maximum one is your compression load. Why? Because during the compression, the firing of your IC engines, it gives more extensive pressure. That's what is going to give you a high compressive force. So it can be due to buckling. You know, buckling, it's in the axial load. During the top dead center position after combustion, you are going to have your total axial force at the maximum, and that doing a compressive force in your piston, and then it is transferred to your connecting rod. So the connecting rod may try to get buckled, getting bulged like things, or it try to bend it along its axis. Buckling is something like forming a wavy pattern and misalignment or moving away from your axis of your connecting rod. So the formulas preferably used throughout the design of connecting rod is: one is your Euler's formula, second one is your Rankine's formula, and third one is your Johnson's formula. So based on your Euler's formula, something called as your crippling load, or sometimes it is also called as your buckling load. The load that is going to buckle, or sometimes it is called as crippling, is calculated by C pi square EA by L by K square, where you can see it is also known as a buckling load. C equal to 1 if the both ends are hinged, and if it is equal to 4 if both ends are fixed, and C equal to 2 for one end fixed and one end hinged, and C equal to 0.25, one end fixed and another end free. So another form is actually you have the pi squared EI by L square, where you can substitute it depending upon the C value, and you end up with a different form. So the equivalent length need to be calculated for a connecting rod before we use the L in the formula to find out your crippling load. So that is capital L equivalent length equal to L by root C, where you see what is your C is already given in the C values are given in this depending upon the type of loading at the end, whether it is a fixed loading or it's a hinged loading based on. So L equal to L for both ends hinged, and L equal to L by 2 for both ends fixed, and this L equal to L by root 2, one end fixed and other end hinged, and L equal to 2L for one end fixed and other end. So these Euler's can be used only for long column, where your slenderness ratio, your length to least radius of gyration ratio is greater than or equal to 80. You can use this Euler formula to avoid buckling. And in Rankine's formula, it can be used for both short and long columns. Actually, the Euler's formula is only used for your long. You need to find out what is the slenderness ratio, and then depending upon the slenderness ratio, if it is more than 80, you can use an Euler's formula. If it is not in the case in Rankine, you can use it for both the things. Both the cases, either it may be short or long column, both the things. And the crippling load can be calculated by 1 by Fc plus 1 by Fe. That is again written as Fc by 1 plus A into L by K square, where A is the Rankine's constant, Fc is the ultimate compressive load, and Fe is the Euler's crippling load, which can be calculated using your Euler. And the third one is your Johnson's formula. So it can be used for short column and ductile material. The crippling load can be calculated by Fc equal to A into sigma y into this ratio 1 minus sigma y by 4 C pi squared E into L by K whole square, where L by K is called as your slenderness ratio, and this is your yield stress and your Young's modulus E, and this is the constant that we use depending upon the type of joint that we have. So the design of connecting rod, it has further 4 parts inside it. First is you need to design of the connecting rod shank. The total shank is starting from the big end to small end. What will be the cross section? If it is an eye, what is the flange width, what is the web width, based on that, what is the length, and that need to be calculated. The second one is your design of connecting rod ends. You need to find out what will be the big end diameter, what will be the small end diameter, what is the thickness of that one, and what is the width of that one. That dimension needs to be attained in the second level. And third one is the design of bolts. Though you have a very good connecting rod, you have seen the marine type or some other type, you may have the bearing to be two halves and you are going to tighten it. You need to understand what kind of strength is needed. Based on that, you need to find out what is the bolt dimensions. And the design of caps. Sometimes if you are using a cap type one, after the bearing is kept inside, you are going to cap it and you need to find out what will be the design of it. So the design of connecting rod shank is made on dimension of I section according to Rankine. FCR crushing is equal to sigma C into A by 1 plus A into L by KXX whole square. It is your radius of gyration along the XX axis. And maximum bending stress can be calculated by the modulus of inertia, modulus of rigidity, and the maximum modulus. And then it is your design of connecting rod ends. You go for the piston pin end. So L1 is the length of the pin, D1 is the inner diameter, and PP1 is the pressure on the pin. So load on the pin can be calculated by all these things, multiplying the pressure on the pin into inner diameter into length of the pin you can calculate. And the outer diameter of the pin is D1 plus 2x, 2 into bush thickness plus 2 into marginal thickness. You can find out what is the outer diameter of the pin. So this is a crank pin end. If its length is L2 and its diameter is D2 and its pressure on pin is PB2, and the load on pin can be calculated similar to the earlier one, like PB2 into D2 into L2. And the outer diameter of the pin can be also similarly calculated by D2 plus 2 into the bush thickness plus 2 into marginal thickness plus 2 into both diameters. So your output will be what? You will be getting the dimensions of your pin, piston pin end and crank pin end dimensions, and you can arrive at this design of connecting. The second one is about your bolts. So the diameter of the bolt, since bolts are subject to inertia forces, maximum inertia force will be calculated at a theta level of your angle 0 will be the maximum inertia force. As I told, it is a pulling force at that time. So you can calculate with for that particular value what will be the inertia force. It is pi by 4 dCp square sigma t into nb, where can be expanded to mr omega m omega r. Okay. Into it is the centrifugal force because of the mass rotating, and into cos theta plus cos 2n theta by n. And in the design of cap, the cap is subject to bending stresses. So the bending stress is equal to m max by z, where mc is the inertia force in the x by 6, and your zc equal to pc into pc square by 6, where x is the diameter of the crank pin plus 2 into bush thickness plus diameter of bolt, and the marginal thickness into 2, where small p is the length of the crank pin minus 2 into flange thickness, where zc is the section modulus. So this one you can see another type of the connecting rod is fully machined. You can see 2 halves, and it has its special preparations here, like different weaving, like what is that? Can be similar to splines on either side, so that it can be fit together to have it's not having any kind of rotary displacement. It will not take place while it is getting tight. And this is another computer design to utilize produce drawing with higher accuracy. As I told you, the output of your design will be a drawing. But nowadays, even in 1980s, in 18th century onwards, what happens? People started using computers for doing their design. So the output will be, instead of having a dimension written and a blueprint or a 2D drawing in engineering, front view, top view, and right side view, nowadays it's being given with a 3-dimensional drawings. So that is called as your computer aided design drawing, and it can has all the features, and it can also be viewed in an assembly view, or you can dismantle and you can see the separately the individual components, and then you can have the design built for individual. So this this is the end of the design of connecting rods. So what are the things that you will find out is the design of your shank, design of your end, your big end diameter, small end diameters, and your bolts and your cap. All these things you are going to use. Meanwhile, I would like to show this kind of a design. My PE project is. Both of you may be thinking that in the morning I was discussing something about the design of what is the dynamics of machines, and what that you are also teaching this subject. Actually, this my PE project is the design of CAM. So you would have studied in kinematics of machines CAM unit or CAM. Hope we have discussed that in the last 3 months before came there. And my PE project I have also discussed in that time, and it is along with that one I wrote a program for this connecting rod design. So it is with your AutoCAD, you know, it's a 3D, you can have any, it's a list processing program where you can do like matrices, you can do some list of values that can be taken into consideration, and it can do some calculations. Both it can make some numerical calculations, and again it can give you a graphical representation or a graphical output. So it is preferred to have one kind of this was my work that I have done. So it's a computer is playing a vital role. So it's a major role to make a design, manufacturing. In design, you have your computer design. So AutoCAD is one of the designing and drafting package. So I'm not marketing for AutoCAD, but at that some 1995 it was my college year 95, 99, 97. It was so popular to use AutoCAD release thing also. So the project was involved with the design of connecting rod for an automobile engine using AutoCAD, visual programming, and something called as your dialog control language. So the program gets minimum number of inputs, such as you need to give the input to that software. It asks for what will be the minimum number of inputs, such as piston diameter. So you need to calculate what is the piston diameter need to be given. Material to be used, you can choose any material. There are different kinds of material. You need to choose what kind of material you are going to use. And then low or high speed engines you are going to use for. And speed of the engine, and 2 or 4 stroke or 2 stroke engine, whether it's for a 2 stroke or 4 stroke engine. So you know that if the 2 stroke, what is the use and asking for a 2 stroke or 4 stroke engine is what is the frequency of loading, the type of loading. In a 4 stroke engine, what you have 2 revolutions, and the piston will be moving twice inside and twice to the top dead center and twice to the bottom dead center. Whereas in your 2 stroke engine, it is going to be in a single rotation. You are going to make all the 4 things happen, right? Your suction stroke, your compression stroke, your power stroke, and your exhaust stroke. All these things are going to be happening. So if you draw the force that is exerted on your connecting rod during this 2 stroke engine and your 4 stroke engine, it will be different. So based on that, you need to design whether it will be having, what will be the frequency of your force, what is the cyclic nature or the frequency of your force, and in what way it is going to increase and what way it is going to reduce. So the program also gives a 2 dimensions. What it will do is, once all these things are given, the design output of the construction details, such as length of the connecting rod, it will be given. So the shank length, and your web thickness, diameter of the big end, and diameter of the small end, length of the big and small ends, and the diameter of the bolts and nuts. And the program also gives a 2D and a 3D drawing model of the connecting rod with accurate dimensions as per your design procedures. So due to the high speed of the computing, you can see this one I don't have a program now, I cannot run it. So this will be the input screen of that one. So I have run it very long back in AutoCAD 2002. Hope you can see this one, right? This is the connecting rod 3D model created by the program. So in no way you are not going to not even use your mouse for drawing this one, not even a single point. So what else you got to do is, you just want to type a program in the command window. You need to type connecting rod CONR. I use a command. So you will get a dialog box like this, and you can even nowadays, if you have plenty of new softwares, you can even create this kind of individual and some programs are already having, some softwares are already having this kind of module also along with them. But I have done it only for one model of your connecting rod. What we have seen is a marine type or your other kind of type we have not tried it. So this one is high speed or low speed, 2 stroke or 4 stroke, what is the diameter, what is the power, what is the speed you can do. And if you press the save to file and if you execute, the program will execute it and you will get something else. It asks for what kind of a material you want. So whatever the type of material I have fed with is something like chromium steels or magnesium or molybdenum combination, all these things with different kinds of materials are given. You need to choose from the file so that the material, each and every material has its own strength, that is your permissible stresses. So depending upon the permissible stress and the stress induced due to your calculations, it will evaluate and then it will give you the results. And this is about the design of connecting rod. It will give an output like this. The length of the connecting rod is 270 mm, depth thickness 8 mm, diameter of the big end in millimeters with 4 decimal places, length of the big end, diameter of the small end, length of the small end, and the diameter of the bolt. Everything will be given. This is a M16 bolt. So as per standard table, it will as well as this is about. Once this is over with the dimensions, you can give a command called 2D draw. So it will also give you a 2-dimensional drawing of your connecting rod in scale, in dimensions, so that you can plot it or print it out directly and you can use it. And a 3D draw command will give you how you can. The 3D draw I have showed you in the first stage itself. So this is your 3D drawing. This is how you are nothing but what I have shown you the. On 8 slides of your design procedures, I just followed it to calculate for do the program. So that's what I told you. A design engineer should not always be like. So it is a design engineer who can design a connecting rod is being replaced by what? A computer program. It's replaceable. So what is your role? If as a design engineer, if you are going to use your design concept, this concept what you are learning is. You are not going to be asked to find the dimension for a connecting rod for this machine, find a connecting rod like that. You need something else other than this. That's why my earlier slides are 20 slides are regarding the types of stresses that is induced. So a design engineer should be more concerned about what? More concerned about the physics that takes place during the action of application. What kind of stresses, what kind of a loading it takes place, in what frequency, in what way, whether the load is continuously happening or whether load is fluctuating, whether there is a compression and the tension forces are together or it is in a repeated way. That is your cyclic loading. So based on that again you have to derive at the dimensions and other things. So once for all, this one is as I told you, not only for this one you can, I have even written some programs. This I would have shown you in your last semester presentation about your so this is about I told you you can even write a program for your cam design. So this is a 2-dimensional drawing of your cam profile, a 3D drawing of a cam profile. So similarly, some other program can be written. So your gearbox design in your design of transmission system you have studied. For that also I have written one program to draw your ray diagrams. And again with the other parameters we calculated number of speeds and other things. And I have even wrote a program for knuckle joints. So this is the knuckle joint design of what are the different kinds of stresses that takes place in the knuckle joint and whether the stresses are less than the permissible stress based on that whether it is allowed or not. You have a overall design is safe or unsafe and it will give you the dimensions and a knuckle joint is also drawn. So why I want to present all these things is see considering a design, right? A design engineering. As I told you, most of the design engineers in India. So I have looked at some of the companies where my students are working as design engineers
some standard procedures are there. They are not going to work with anything else. But the thing you want to see is once the design is getting failed, then only people trouble you, right? The design, why your design is still we have some what is that? Some consultancy work we are doing for Rane. You know Rane Industries. They are earlier they called it as Rane Steering. Right? They used to the steering end they used to, and then they started working with the Rane brakes. Now they have all the automotive components that they are working with. You know that what is that Tata AC Sinayana. So exactly they have the steering end was manufactured by Rane. What they have done is I don't know whether they have shared this one. So they brought me one or two bearing ends. Actually, Tata company is asking the Rane Industries to supply this steering end. You know steering end, if you are rotating a steering, and there will be a steering box and a steering gear that will be connected in a gear assembly, so that there will be another 4-bar link that will be moving like this. And this 4-bar link, this link is connected with your wheel, so that it will be only allowed to move left or right. So what happens is this steering end, these two ends are need to be hinged by means of a steering end, which is to be lubricated. There will be one or two balls will be rotating one inside another. And what they did is they produced around 4 lakh components or something as they told, and they based on the design and drawing they created, and they have supplied the components. In 1 or 2 months, what they got is around 4,000 component of that steering end got failed. Everything was taken in a box and they thrown in their face. They told your design is something wrong. So they have given the dimensions. What is the part of the design engineer will arrive at this material, this drawing I need at this condition, and this is the surface finish that I want. That might be our input that they have given to the manufacturing unit. And they, without thinking about what it is going to be done, they have done the things. So what the problem is, actually I was one of the person we were thinking about the solution for the problem. And easily I could understand. What I did is, actually I asked him to bring that. He told it is failed, we are rejected, it is failed, we are rejected. So I asked him to bring a failed component of that. So I took it and it was very clean. It was really clean with water and oil, and it was new, looking very clean. I saw there are plenty of scratches, right? Scratches on the ball end. I find plenty of scratches. See, a smooth surface to smooth surface. If it is going to work over there, what is the use of getting a scratch? I asked him how it is getting scratch. What kind of a thing that you will do? They told that, so have you ever opened it and filled with any other lubrication so that some contamination are there in the surface? He told it is a closed lubricated end. What is that? It's a closed lubricated end. When it is manufactured, they have a cup, they will open it. It is a pressure pressed plastic cup inside which they pour the grease or semi-solid lubricant, and then they close it. So I asked them, in what way it is disconnected? Have you taken any photograph? What is this one? This is something called as your post-mortem. After a failure is there, you need to take a photograph of before it. They told that we have not taken any photograph. So without taking photograph, what you did, we simply dismantled and then we looked at the things. So then I made somebody to look at if there is a failure, you bring it to them, and you need to open and look into that what kind of things happen in the failure, why it is got failed. And at last, what I could observe is what happened. This vehicle they are using in any nearby the seashore also, like Nagapattinam or some easier roads they are using, where you see there are plenty of river or sea sands are available on the roads. This you know that one shining black particles of sand, what it is called as? They are what? Silicon carbates. Silicon carbates are very strong particles. What they did is, once they are traveling during the rainy season or in the wet conditions, the silicon carbates gets entrapped inside the box, and that too the box is not so good to withstand. It was found broken, and with the grease they added this abrasive particle. You know, an abrasive listening. So these are abrasive particles that get entrapped between two sliding contact surfaces. That's why you see in your diesel engine or your petrol engine inside your combustion chamber, you have plenty of filters. In your diesel, you may have very fine antagonism. That's what you have a filter for that diesel filter. You filter the diesel and they make it as pure as possible. Then you inject it through the. One is it will get blocked with your nozzle. And other thing is if you have any foreign third body abrasive, this is called as your third body abrasive. Then I told them just to replace the cover. So they replace the cover. Now all the components are again taken back by the company. So this is the design. See, when you are going to make a design, you need to look at not only the forces acting, but the physical, environmental things. So we don't want. That's what I told you. A design engineer cannot be replaced by a computer. If you think more than a computer, how do you think more than a computer? You need to understand if the same kind of a joint is made for a different equipment or a different automotive engine, where it is going to be useful. So I will show you certain slides that will tell about some of the design failures, right? So this is regarding, hope I think your professor might have given you your PhD data book and you know all the procedures for the data. So I asked the permission from your teacher to give you a different view in your design. I was asked for when I was handling a design subject in my interview for my professor candidate. I was called for what they asked is what are the different kinds of failure. They asked me what are the different kinds of failure. And I told about some of the failure criteria. They asked about, see, because engineers should always understand about what kind of failure will take place and what can be done before to prevent them. That is one important. So this is something called as your failure mechanisms and fractography. As I told you, it is like the post-mortem, right? After something is getting failed. So how to look at and what you are going to do, what can be done. So I just went for a course. I attended a course regarding material design and selection of material and how to identify what is the type of failure in the material and how to give some corrective action. So I got impressed in this field and now right now I am working in this area in my in my for some of my PhD students I used to do this work also. So you know a tension test or a compression test or something else we do to test a material. Once it got failed, most of them what they do, this material got failed at this temperature, sorry, at this load, at this thing like that they used to write. But what I do is when I get that failure, I take the failure to some kind of a different kind of a study and I find why it got failed. So that will be my thing. So that is the plus point that I have in my research and I have some publications people are talking about. So this is, you see, the fractography or fracture failure mechanisms characterization is, you studied material science? Have you studied material science? Material science? Yeah, you studied material science. So you know about what is a microstructure, right? What is a grains, how grains are formed in a material and how the microstructure takes place. So what they do is, this is something called as your macro view, right? You just after getting something failed, I told you, you look at the failure and you need to understand what has happened, whether there is what kind of thing might have happened when it is getting failed. The second one is, if you could not observe with your eyes, you don't have a zoomed magnification eyes, you put a small piece of the failure area, put it under microscope, maximize it and look at whether you can see something else. That too, if you can't find it out, you put it under some energy dispersive spectroscopy. What you do is, I need to find what are the elements that are available in the failed region, right? Actually, this is most probably used in aerospace industries. That is called as your aeronautic aircraft crashes. If there is an aircraft crash, right? You know, if your bus or some your engine is getting damaged, if the vehicle will stop. You can open the engine and you can see where the fault is, then you correct. But in a flight, if an engine fails, right, what happens? The total flight will fall down and it will get crashed. But you cannot, there is nothing else left to you to understand what kind of failure. So that's why people used to take the black box and hear what somebody is speaking. There is a smoke, somebody is crying, so there is an before the explosion there was some firing. And they can tell that, see, the oil level is down or something is shouting. and based on all the other records are there, based on that they used to identify what kind of it is. So, but after the failure is, they are taking all the components from the failed area. They used to do this kind of. So I can understand the material. You are talking about a design of with a particular material being selected, but you should be sure whether the material is in the same form as if you have started using. Okay, you are using a material with different elemental combination composition, and after the failure you should be aware whether the same composition exists. Otherwise, the property of the material might have changed, and that would have given you some failure. So, what we can look at is classification of fracture features, identification of fracture modes, application, examples for fracture analysis, and this will be my presentation. So, what is fractography? Is the study of the fracture surface of material. So, I am going beyond your design. So, it got failed. So, you are going to look at a micrograph, that is called as, since it is the broken piece is seen in a micrograph, it is called as a fractured piece is looked over a micrograph, it is called as a fractograph. So, this is nothing but the signature of the fracture process and characteristic features. It is a signature. How it has failed will be seen from the fractograph. And the examination of the fracture surfaces to determine the mode of failure. So, your first unit, what you studied, what are the different kinds of stresses that it is induced. So, we see everywhere, I was talking about the connecting rod. When it is in the top dead center, it has the fully axial compression load. But it is by mechanics I am explaining. But actually, will it happen? Will it be the maximum load? Is there anything we measured during the operation? We are not going to do it. But then what will be the maximum temperature? I might have predicted. I have not measured anywhere else any probe what is the temperature that's being generated during the working of the engine. So this macroscopic features you can see at the examination of the fracture to determine the reason for the failure. You can look at the smoothness and markings observed with the naked eyes or optical microscope. That is called as the macroscopic feature. So if you break it, if you have whatever you do, you take a chalk piece and if you break it and you look at the chalk piece very closely, how it looks like. Have you seen a chalk piece breaking a chalk piece very closely, how it will be? So again, have you kept the chalk piece again over the broken place? You have it tried? So it can be you can even get there is no elongation, right? Once you break the chalk piece and again if you put it in its original state, it will be of same length. There is no change in the deformation. That is what does mean. What does it mean? It is a brittle failure. There is no ductility at all. There is no ductile failure at all. So in that close view, if you look at, you can say that it's sometimes what you do, you take a piece of aluminum and then you pull it, or you bend it or break it, you break the fracture. Then if you look at whether the cross section meets, again if you put it together, can you see the length will be same? Some ductility is there. So this is like so you can look at what kind of a failure it is by your naked eyes. You can find what kind of a failure it is. Next is microscopic features. You look at some microscopic details to understand furthermore. And the mode of failures be, right, your fatigue, stress corrosion cracking, hydrogen embrittlement, or reason for crack initiation. So this is again important, right? In 1970s, I heard there was a flight crash, right? The design is perfect, but at last they could not find out that you know your what is that Titanic ship failure. So if you know what kind of a design failure it is, material design, and I don't know, remember whether we have discussed that also. It is something called as ductile to brittle transition temperature. If you take any material and put it under sub-zero temperature, that is your cryogenic temperature, you put you even under a refrigerator, what is that? Very low temperature, freezing temperature. The material, if you break the material, it will behave like a brittle. You take aluminium, you bend it, you put it under somewhere else, and if you bend it, it will break like a chalk piece. Or if you put it in a furnace, if you break it, it doesn't work like that. So that is how you can see there will be there is a reason, right? The crack initiation, how the crack started. that can be seen from that one, stress concentration or material defect or corrosion itself. So this is you have studied fluctuating and non-fluctuating stresses. I told about this is very important, right? Your design further to arrive at the dimensions, you should be very clear about what kind of stresses will be acting on the component. So what is your so that is your non-fluctuating stresses or fluctuating stresses. So mechanical, thermal, chemical and thermal. Three effects. Mechanical stresses are there, and there will be stress created by thermal, and there will be chemical. Chemicals are also, it's going to give you corrosive environment. So you have exposures of any metal, you have these kind of different kinds of modes of stresses are there. So in a non-fluctuating is like a mechanical or a tension, a complete tension or a complete compression or a bending or a complete torsion or your shear stress, right? Or your shearing, all these things comes under your non-fluctuating stress. And in chemical, stress corrosion, hydrogen embrittlement, and in thermal, creeping. You know, creeping, if you keep on loading without removing the load, if you are allowing it for a very long time, automatically it will get elongated. Have I shown you any material regarding this one earlier? So there is some kind I told about material behavior, right? See, so because people start manual, right? I want to show some movie. That's why in the afternoon I am changing my area, right? See, this is material, right? I am going to give what kind of load I am going to give. It's a tension. So in tension I have taken this. You can see this one, right? Again, if I keep it there, I am finding the same place. You see how it looks like. Fracture is flat, right? It is very flat. What it is like that your chalk piece. How your chalk piece will you see any ups and downs are there? You like that? See this chalk piece. You can see the surface is flat, right? It is flat like chalk piece, what we call it as a right? There is any reduction in the size? Yes, any reduction in the size? No, it is of same size, right? Somewhat same size. So again, the non-material, I will tell you later. That will be the conclusion. What is this? What is this one? Ductile. Super plastic. Call it as super plastic. Without applying any load, if it gets deformed, please listen carefully. So this is something like so what is this? Load is without applying any load. Without applying any load, I have the dimension. See, without having any load. That's what I am talking about. Not thermal creep. What happened without applying it in due course of time with the same load, without increasing the load, with a constant load. With a constant load, if you keep it for a very long time, it keeps on extending. The same material I showed you some time before. How it was? If there is no change in the length, and if it is getting easy, I am not using my nails, right? Right? So now it is not behaving. Any idea about this behavior? This material is behaving properly, differently. Any idea you can tell about this material? So please add some sentences about this material. Now I use flexible. Flexible property of material. Material. Okay. Now there are 10 to the power of 2 material properties. Oh, 10 to the power of 2 material properties are there in a material. What are these? Somewhat related. What is this one? You clearly told something. Ductile. It is severe plastic material, ductile material. So ductile material, what is ductility? And one more thing I forgot to tell that, see, this I am applying the force rightly, it's getting whatever the plate like chapati is malleable material, right? It is malleable. It's made to be a plate, I can use it. It's malleable material, I am making it into plate, right? It's a severe plastic material. One more property is missing. What is the property? He told the property. He told the property. All these things are connected not with this one is your design. The materials behavior at a different what is that? This is a different strain rate. We call it as strain rate. See, now I will tell you the fact. What are the things? If I quickly apply a force, that is a quick application. That is the strain rate is very high. Rate of change of dimension is very high. That is, I am going to quickly apply a load. It is not at all changing, it behaves like elastic. The rate of change of displacement is done in a very high way. It is behaving like elastic. And this is the same way if it is a pull force. If I am giving the rate of change of dimension at very high speed, it works like a brittle material, so that it is so flat, you can again stick to that and you cannot find out whether it is broken or not, like a chalk piece. If the rate of change of dimension is very slow, it behaves like plastic. So this is something called as the behavior of the material with strain rate sensitivity. What is that? Strain rate sensitivity of a material. You have studied this in your material science. This is, every material has this kind of a quality. The chair you sit on the metal plate, it has the same kind of strain rate sensitivity. But see, the different strain rates for this material, that is, I am capable of doing that. A human can capably do a strain rate with this force is enough for making a slow strain rate or a quick strain rate. But in case of an aluminium, it has one strain rate. In aluminium, it has one strain rate at which it will become very like this, fully plastic. So that will be the strain rate will be like, in that way I have to stretch it for 1 meter. So that is something called as high velocity forming. We call it as high velocity forming. How can it be done? I make a small cup of an aluminium. I put a cup, inside that I keep a bomb. Atom bomb. I close it, switch it on, I ignite it. It explodes. Within a sudden explosion, it can be sometimes become like a balloon. You understand? That's it. That strain rate I cannot do it in hand. That's what aluminium I cannot. So every material you should be very cautious that every material has different strain rate. It will behave different. So that's how I am talking about this one. So your design. We are not at all talking about in a design what kind of a material property is important is also this. But as I told you, once I do the failure, so now I can ask you what kind of a failure. You can tell that this is a ductile failure. It gets elongated and then it got failed. If I am applying it quickly, you can observe that it is a brittle failure. It is not getting any plastic deformation. it is whatever the link before its failure is there, then it is called as a brittle failure. If I quickly deform it, it's similar to that of it is giving you a high elastic behavior. So we are back to this story like fluctuating stresses. So this will be a mechanical or overload fatigue, high cycle fatigue, low cycle fatigue, fretting fatigue, wear. So loading, so your stresses, see, as I told you, what kind of a stress I give? It's a quick stress, right? It's a tension stress I am giving in a quick way. I give a compressive stress in a quick way. So you can apply stress in different forms. So your physics will be different. Your object or the component is going to be getting exposed with different kind of stresses. We don't have a knowledge enough to read what are all the stresses that takes place. That's what we have some finite element, magnetic or something else. Other than that, we should be very clear enough what kind of stress that it is going to take place. So a design engineer is supposed to know about what are all the different kinds of stresses. Like a fluctuating stress and non-fluctuating stress. So in a fluctuating stress, what you have is fatigue. What is fatigue? Repeated compression and tension applied in cycles. For example, I take for 1 minute, I apply compression and tension. 10 times I compress tension, compression, tension. I make it for 10 times. I can make it for 100 times. I can make it for 1,000 times. I can make it for 10,000 times, depending upon. For example, you imagine there is a shaft. That shaft is rotating at 20,000 RPM. The shaft have a small bend. Right? Shaft have a small bend. So, but the force is together. So, what happens when the shaft is coming down? The top portion gets compression, and the bottom portion gets tension. When the shaft is coming up at the top position, the upward the portion at the top getting tension, and the portion at the bottom getting. You understand? So fatigue, how we do fatigue testing is we take a rod, we bend the rod slightly, and then we keep on rotating for 10,000 RPM or 5,000 RPM we rotate. That is fatigue loading. Then we look at how many number of revolutions is getting rotated before it gets failed. That is your fatigue testing. So fatigue is, you call it as a cyclic, high cycle fatigue, low cycle fatigue. For example, you imagine an aeroplane. The aeroplane has a wings. So if you have traveled in a flight, if you are sitting in the nearby window, you can see how your wings will be. It will be like this. Actually, it's not rigidly, it's not going. You should see that. When you first time if you travel nearby, sit nearby the window, then seriously you will not, you will get everything right. So you will be afraid. I have even got sweating. First of all, the weather, I found that it is a fault. One wing is shaking. Then I asked him just to go for a restroom, and I see the next wing also. That was also, so it is something quite, it's a flexible, right? But you see the portion fixing over here is what? Repeatedly acting with compression tension. That is fatigue. What is the frequency with which it vibrates? Serious. So that's why aerospace engines, all the components, any material that is going to be used in an aero engine industry should be having a very high fatigue strength. So how to do a fatigue test? How they do? They take a block of material. They take in one calculator, let us imagine a block of material. Right? They take a block of material like this. They put one hole here. They put another hole here. They make a V groove here, and there will be a small cutting over here. So this one, they do like this. Actually, there will be a small cut or a very slim hole they will make, and they will move like this. That is, they compress and tension. They compress and make tension. Compression and tension. There will be a small crack. Why the small crack is without making crack? If they do compression and tension, he has to go for 1 year or 2 years to complete the test. If there is a small crack created, that crack will keep on propagate and the material will get failed. That is where that the cycle in which in 1 minute how many times you do is called as your low cycle fatigue or high cycle fatigue test. But I don't know. See, I got what happened on aeroplane when it was flying at a particular level. It got exploded. It got fell into the sea like what happened 1 month before. Now I could see that one of the wing is dismantled half. So I should know about what kind of a stress has created the failure. How to find out whether what kind of a failure it takes place. So what we do is, so these are the fractures. In mechanical loading, right? If you apply mechanical loading, what? You have ductile, brittle or fatigue failure. And in environmental, you have corrosion and erosion. Voids are created, one crack is created. That crack will get, and it is something called as your facets. It will look like flat crack at its appearance. What you see in a ductile failure is what? Dimples. But in a brittle failure, you will see only flat facets. You can see here, see this one is here, cleavage fracture. Can you see this one is different from these microscopes? What is this one? It is like something, you can see some plasticity has taken place before its failure, but you see here there is no plasticity. Because this is a closed look. If you look at a chalk piece, you will look like this. The grains will be getting separated. One grain, very fine powders are getting one over the other, or very fine grains one with the other, it is getting embedded. So in a fracture, what happens? There is no plastic deformation. That means there is no change in the dimension, but the crack will go inside. Only a crack will separate, and it will make it into two pieces. Again, if you keep it in the exact position, it should look like the same piece without any fracture. So you can even use your a Fevikwik to what a brittle material to paste it material, so that it won't show you a plastic deformation. So this is a progressive failure. But see, in a brittle failure, these kind of failures like fatigue or stress corrosion cracking or hydrogen brittlement, these things are progressive cracking. I told you that a ductile failure will show you that it is going to fail before, but a fatigue failure is also a progressive failure. But it is not giving much time to look into that whether it will take place. But you can see it very closely. If you find any micro crack on the surface, instantly what you need to do? You need to stop using that material, or else you have to remove the micro crack on the surface. So that's how you can see here. Please look at this image very closely. There are different regions. It is looking like a, what is that? In a seashore. In a seashore, it's looking like the sea water will come and go inside. You can see a layer by layer of material with different colors. That is what we call it as chevron marks. You see here a different kind of grains is there. Here some successive lines are there. Then you can see there will be a dot or different color over here. So with this one, a person who is having a good knowledge in the failure analysis can tell you the crack has started from here and it has traveled like this, and these are all something. This material is called as silly putty. SILLIPUTTY. You please Google it and you can find what this material is. It is in an American research lab. Accidentally they have come up with this material. It is something a silica based, clay. Children used to play in a clay. So when they are preparing in a laboratory, they come to know that this material was behaving differently. So they patented this material and its composition, and they are selling it with the name silly putty, like this container, right? This kind of container. You can search through internet. I bought it in somewhere in Singapore. It cost around $11, around 600 rupees or something.